In this video lesson, we're going to begin Unit 8, where we learn about organic chemistry. Soon we are going to rename this to be our Biochem Part 1. As always, as you are following along in this lesson, I ask that you pause the videos and try and do the work on your own, and that you also watch this on either your phone or your computer, so that way you can follow along and take notes on your iPad. Before we delve further into this unit, I do want to take a moment to remind you some basic properties of chemistry. So compounds are composed of nonmetals, that is, elements on the right side of the stair-step line plus hydrogen up here, are covalent compounds, and their atoms share electrons in order to achieve their octets. Please remember that elements want to have, and it's the octet rule, oct meaning 8, they want to achieve 8 valence electrons. That is, they want to have full S, and S are these first two columns here, so they're groups 1 and 2, and p orbitals, and that is these groups 13, 14, 15, 16, 17, and 18. So every element wants to be like a noble gas. They want to have 8 electrons in their outer energy level. So what organic means, or what it references, is compounds that are composed of carbon and hydrogen. And a lot of us have heard of the term organic life. And in order to live, or every living thing that we know of consists of carbon and hydrogen as primary elements. So in today's unit, we are going to focus on hydrocarbons. That is, compounds composed of solely hydrogen, hydro, and carbon. So hydrocarbons. Alkanes are one type of compound that we're going to learn about, and that means they contain all single bonds. So before, when you learned about Lewis dot structures, you would see structures sometimes drawn like this, and this would mean that everything has full outer energy level, because remember, each bond here represents 2 electrons. Sometimes you would also see something that has to be double bonded, like when I would ask you to draw O2. Well, that would mean that every individual oxygen atom wants to have 8 valence electrons. So in order to do that, you would have to have a double bond on there, and then each oxygen would have to have 2 lone pairs. That would mean that this lone pair is giving, this lone pair is giving 2 electrons, that's 2 electrons, and then each bond is 2 electrons to this oxygen, and then again that's 2 electrons, 5, 6, 7, 8. So now each oxygen has 8 electrons, therefore the octet rule is satisfied. And something like this would be an example of an alkene in a way, just because it has this double bond here. And then before, when you saw a triple bond, that was like with nitrogen. So each nitrogen would go like this, and they would have 8 electrons as well. And again, as we get further into this unit, it will start to make more sense. But nitrogen would, in a way, be an example of an alkyne, just because it has this triple bond in here. As we get further into naming these, or drawing the structures of hydrocarbons, you'll see that they have a prefix, which indicates the number of carbon atoms in a hydrocarbon, and then the ending, which is this ane, ene, and ine, indicate the type of hydrocarbon. And this slide goes over the prefixes. So before, when we were learning how to name compounds, we often saw prefixes like mono, and as you can see down here, we had mono, di, tri, tetra, and so on. Well, you'll notice that these 4 first prefixes have now changed. And that's why on the periodic tables that we use in class, you will see that there's the Greek prefixes and there's organic prefixes. Up until now, we only use these Greek prefixes. Now we're going to start on the organic, and the first 4 are the only ones that change. So 1 is now meth, 2 is eth, 3 is prop, and 4 is buta. And those are the prefixes, and then we also have our ane, ene, and ine ending. And the way that I remember the difference between ane, ene, and ine is I just think of their way going through the alphabet. A comes first, and that is a single bond. E is later in the alphabet, and that is a double bond, and then Y is even later in the alphabet, and that is a triple bond. So if we want to name an alkane, that is a hydrocarbon which all carbon atoms are connected by single bonds only. So that could be like a carbon bonded to 4 hydrogens, or it could be this really long chain of carbons, but they are all single bonded. And generally in a hydrocarbon, especially through today, carbons will only ever be bonded to hydrogens. And so I could go through and fill in the hydrogens on each one of these. And if you remember how we do our Lewis dot structures, we first have to determine how many valence electrons every element has. So please remember, hydrogen and anything lower will have 1 valence electron. Beryllium has 2, boron has 3, carbon 4, nitrogen lower 5, oxygen lower 6, fluorine in lower 7, and then the noble gases, helium has 2, and everything else has 8. So carbon, if we draw that out, carbon would look like this. And remember, when we do our Lewis dot structure, we place 1 electron at a time, and we pretend that every element has 4 sides. And then after every electron has been placed individually, then we can start to pair them up. So carbon wants 4 valence electrons, or if we look at, say, nitrogen, well, nitrogen, and we'll work with this in the future, would have 1, 2, 3, 4, and now that I've placed 4 single electrons, now I can go through and pair one up. And for every single electron that an element has, it wants that many bonds. So carbon wants 4 bonds, and nitrogen would want 3. And if we go ahead and draw hydrogen, well, hydrogen only has 1 valence electron, as you can see up here. So if we draw that, that means that hydrogen only has 1 valence electron, and therefore it wants to form 1 bond. And that works out really well if we look at our structure down here. So carbon wants to have 4 bonds, each hydrogen wants to have 1. And if you look at this, our hydrogens all have 1 bond, and carbon has 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So every carbon is happy and every hydrogen is happy. And as an example, if I were to go through and name this particular structure that I've drawn, I have 1, 2, 3, 4, 5, 6 carbons. So if I look at my prefixes, 6 is hepta, and so I would name this as, I'm sorry, not hepta, it is hexa, so I would name this as hexa, and then I need to look at my ending is ane, so this would be hexane. So I have my prefix here of hex, and I have my suffix or my ending of ane. That means 6 carbons, and this ane means that they are all singly bonded. And we will get more practice on the next slide. And in class you've often heard that our gas jets have methane come out of them. Well, meth is now our prefix for 1. And so if we go through and do this, then that means that we have 1 carbon. They're all singly bonded because of our ane ending. So we place our 1 carbon, and then we would have our 1, 2, 3, 4 hydrogens. Again, the name tells us nothing about how many hydrogens there are. It kind of does, but we can just add our hydrogens on at the end. So if we go through and name ethane, well, our structural formula is like this, and I'll go through and do those first, and then I will show you what a skeleton formula is. They're the same thing, it's just a different way to draw structures. So if I draw the structural formula for ethane, well, first let's go through and figure out, well, we'll draw a structural formula first. So here we draw 1 carbon, because we have ethane, and then we have to draw a second one because our ethane is our prefix for 2. So those carbons now only have 1 bond each, so how can we get them to have their 4 bonds that we want? Well, we have to add on our hydrogens. So we'll add on our singly bonded hydrogens here, and now we will have 2 carbons. They're all singly bonded, and therefore we have ethane. And now it wants us to write the molecular formula as well. When you write a molecular formula, you're pretty much always going to write carbon first. And so we would have C2, because we have 1, 2 carbons, H6 because we have 1, 2, 3, 4, 5, 6 hydrogens. And now I would like you to please pause the video and try and draw propane and butane on your own. Alright, now that you have tried both of these, let's go through and draw them. So propane, prop meaning 3, we would draw this as carbon, bonded to carbon, bonded to carbon. So we have our 3 carbons, and then we just need to add in our hydrogens. And please note this carbon, since it already has 1 bond here and 1 bond here, it only wants to have 4 total bonds. So therefore this carbon is only going to have 2 hydrogens attached, and this carbon down here is going to have 3 of them. And then if we look at butane, butane is the prefix for 4, so we're going to have 4 carbons singly bonded. And now again we need to add in our number of hydrogens. So if we look at each carbon, and for some people it's easier to do it this way, we look and we're like, alright, this carbon has 1 bond, this one has 2, this one has 2, this one has 1. So how many does each need to fill and be happy with its 4 bonds? Well, this carbon down here is going to need 3 more bonds, so those are all going to come from hydrogen. This one already has 2 bonds, so it is going to only need 2 more hydrogen. This one has its 2 bonds already, so it needs 2 more, and this one is going to need 3 more. And there's our structure for butane. You'll also notice I switched from drawing these as just like straight lines to having this bend in here. This bend is just to save room. It really doesn't matter which way you draw it. If you wanted to draw, say, propane as carbon bonded to carbon bonded to carbon, either way is fine. I generally just prefer to draw carbon to carbon to carbon because it saves room. Alright, now let's go through and actually draw what is called the skeleton formula, as you can see here. So if I draw my skeleton formula, what this is it actually is just assuming carbons and hydrogens, and it makes life a lot easier. So if I wanted to draw the skeleton formula for ethane, it would look just like this. Because the way that works is that every end point of a line, it is assumed a carbon is there, and then we can actually assume the hydrogens as well. Or if I were to draw the structural formula for propane, it would just look like this. Because we are assuming that I have a carbon at this end, and at this end. And then we can actually assume all of our hydrogens as well. Because every bond that isn't to a carbon is to a hydrogen. Or if we were to draw the skeleton structure for butane, we just have 1 carbon, 2 carbons, 3 carbons, 4 carbons. And our bond is good. Oh, and one more thing we should have done on this slide is come up with our molecular formula. So we go through and count, and we'll start with propane. I have 1, 2, 3 carbons. So we're going to draw this as C3, and then we count our hydrogens. And we have 1, 2, 3, 4, 5, 6, 7, 8. And so this would be C3H8. Or if we look at butane, we have 1, 2, 3, 4 carbons, and we can start counting our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the formula for butane would be C4H10. And that is an example of how we name alkane molecules. If you would like extra practice, I ask that you please go onto the Moodle page and try assignment 8.1. Next we will focus on drawing alkenes and alkynes, which are going to be very similar, so the notes will start to move along a little bit quicker. As you saw a couple slides ago, we like to come up with molecular formulas for the names as well. And so to do this, it can be a little daunting to go through and draw out all of our carbons, especially when you get into really, really long carbon chains, and then go through and draw all of our hydrogens and then count them. So what I would like you to do is actually go back a couple slides and see if you can come up with a mathematical relationship between the number of carbons that there are and the number of hydrogens. I would recommend please pausing the video and see if you can come up with this formula. Alright, now that you have tried to come up with this formula, let's go through and work this out together. So we know that propane, for example, was C3H8 and butane was C4H10. Well, if you go through and look at this, you'll notice that the number of hydrogens ends up being twice the number of carbons. So if we take 2 times 3 plus 2 more, and that gives us our 8 hydrogens. Or if we look at butane here, we had 4 carbons, we multiply that by 2, and we add 2, and that gives us our 10 hydrogens. So the formula for this, and this only applies to alkanes, this does not work for alkenes or alkynes, is CxH2x plus 2. So using this example down here, what is the molecular formula for a 25 carbon alkane? And this is actually candle wax, or a lot of candle waxes. Well, using the formula, we can see that we have 25 carbons, so it would be C25. And then our number of hydrogens is 2 times 25 times our number of carbons plus 2. And that means our molecular formula would be C25H52. And yes, there are carbon chains that are this long. They don't really have a name. They don't have prefixes for every single number. So this is a much easier way to come up with a formula for this rather than drawing out a 25 carbon chain. Now we're going to start focusing on alkenes. Alkenes are hydrocarbons in which one or more carbon atoms is connected by a double bond. And double bond here is the key word for alkenes. So when you do this, you want to use the prefix to indicate the number of carbon atoms in the longest chain. So there are different types of chains. They're not all just single bonded carbons going the whole way through. Sometimes you will actually have carbons that branch off like this, or you might see a branch that goes like this and then this. And we will get practice with that coming up here. So the rules for this do change a little bit. Now we use a prefix to indicate the number of carbons in the longest carbon chain, and what that means is if I just count my carbons going straight across here, I have 1, 2, 3, 4. However, that is not my longest carbon chain. If I look at this one, I could actually start with this carbon and go 1, 2, 3, 4, 5, or going the other way. I could actually go 1, 2, 3, 4, 5, or like this, 1, 2, 3, 4, 5. So going straight across like this is not necessarily going to give us our longest carbon chain. You also need to use a number to indicate which carbon the double bonds start from. If there's only one and it is located on the first carbon, no number is required. So again, that's like often in chemistry when we just leave the one out. And then we have to use an -ene ending. And as always, this might seem very, very confusing. It's a lot of different rules being thrown at you. But with practice, it starts to make more sense. Alright, so if we go through and draw out ethene, well, we can draw this as F meaning 2, so we have 2 carbons, and then ene meaning that they are double bonded. So now this changes up how our hydrogens work. Because before these carbons would have needed 3 more hydrogens, but now they already have 1, 2 bonds, so they only need 2 more. So we're just going to go through, oops, sorry, that should be a straight line, and add our hydrogens on there. But they only need 2 more hydrogens to make their 4 bonds that they want. So now if I go through and count, these hydrogens have their 1 bond each, and then I can count the carbons has 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. Because as we talked about in the first slide of these notes, electrons are shared in covalent bonds, so these bonds count for both this carbon and this carbon. And as always, we want to go through and find out our structural formula. So now we have 1, 2 carbons, and 1, 2, 3, 4 hydrogens. So this molecular formula would be C2H4. Or if we draw the skeleton formula for this, and usually you don't use skeleton formula for shorter structures, but it would just look like an equal sign, because it is assumed that there is 1 carbon here and 1 carbon here. Now if we look at our alkenes, you'll notice that we're getting into a different pattern here. And this is going back to last slide when it talked about having numbers in there as well. So this has 1,3-buta, and you'll notice we also have this prefix in here of di. So the way that this works is there is a double bond. Since this is an ene ending, it means that there is a double bond on both the first and on the third carbon. And this buta means that we have 4 total carbons. So what I'm going to start off doing is just drawing 1, 2, 3, 4 carbons. And then I'm going to put a double bond indicated by our ene ending on the first and the third carbon. And so and you can number from any side. If you want to make this one, you can, or if you want to make this one, you can do that as well. I usually like to just start from the left side. So if we do this, I'm going to put a double bond on carbon 1, and I'm going to put a double bond on my third carbon. And so right now I have this as carbon 1, this as carbon 3. Now we have to go in and add in our hydrogens, so let's figure out how many hydrogens we need on each carbon. This carbon has 2 bonds already, so this one's going to need 2 more. This carbon already has 1, 2, 3 bonds, so it's only going to need 1 hydrogen. This one has 1, 2, 3 bonds, so it will also only need 1 hydrogen. And then this carbon has 1, 2 bonds, so it's going to need 2 hydrogens. So if we draw this in, it is going to look something like this. And again, it doesn't matter too much where we draw the hydrogens. You usually want to be symmetrical and draw at 90-degree angles. 1 hydrogen there, 1 right here, and then we have our hydrogen down, hydrogen here, and there we have all of it. And if we go through and count to make our chemical formula, we have 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6 hydrogens. So this would be C4H6. Or we can draw the skeleton formula, or skeleton structure, sorry, and it would look like 1 carbon, 2, 3, 4. And now the way that we draw double bonds is just by adding another line in there. And again, we want to make sure we draw on the correct carbons. So if we do this, we have our carbons 1, 2, 3, 4, and I'll just label these so maybe you can see them a little better. And now my bonds need to occur starting on the first and the third carbon. So first and third carbon, and this double bond is going to look like this. So this double bond starts on the first carbon, goes to the second. This double bond starts on the third carbon and then connects to the fourth. Now if we go through and draw propene, well, propene has the prefix of prop, so therefore it is going to be 3 carbons. And since there's no indication of the placement like we had up here, we can just assume that it is on the first carbon. So we're going to draw a double bond in there because it is that ene ending. We need a double bond. And we need to add in our hydrogens, so we're going to have 2 hydrogens on this carbon, 1 hydrogen on here, and then this carbon is actually going to need 3 hydrogens. And so if we go through and come up with the formula for this, it would be C3H6. And here's a big challenge for you. See if you can go through and find the error with the name in 2,4,6 heptatriene. And I will give you a minute to pause the video and then try that on your own. Alright, so if we go through and draw this one out, and I'm actually going to start just drawing skeleton structures now because they are much, much easier and quicker to do. So if we draw this out, we have the prefix of hept or hepta, which means 7 carbons. We have ene, meaning we're referencing double bonds. And then we have a double bond on the 2, 4, and 6 carbon. Also, please note what this tri here means is it references how many double bonds there are. So here, tri, and we have 2, 4, 6. Or up here we had di on the first and third. So that means we had 2 double bonds. This tri means we're going to have 3 double bonds. And when you do that prefix, it always has to go before what's indicating or what type of bond it's going to be. And this will make more sense when we get into future days and we have different types of endings. So if we draw this one out, this has 7 carbons, so 1, 2, 3, 4, 5, 6, 7. And we draw on our double bonds on the second. So let's go through and number these really quick. I'm just going to say this is 1, 2, 3, 4, 5, 6, 7. And if we draw our bonds in, we're going to have a bond on the second carbon, starting on the 4th carbon, and starting on the 6th carbon. And if you got the error correct, I would be impressed because I haven't talked too much about this yet. But when you're numbering, you always want to make sure you have the lowest possible numbers up here. What that means, and I talked about this before, is you can start counting from either side. So I could go 1, 2, 3, 4, 5, 6, 7. Or I could count this as 1, 2, 3, 4, 5, 6, 7. And you'll notice if I start from this end that I can actually, and I'm going to go through and erase my numbers here. So we no longer want that 7. So if we get rid of these numbers and we draw in some new ones, this actually becomes 1, 2, 3, 4, 5, 6, 7. And you'll notice that changes these numbers up here to not being 2, 4, 6, but our double bonds actually occur on the 1st carbon, 3rd carbon, and 5th carbon. So the correct name for this should be not 2, 4, 6 heptatriene, but it should be 1, 3, 5 heptatriene, because you always want the lowest possible numbers in your name. For extra practice, I would look at the assignment 8.1 hydrocarbon and try some of those names out. Now we're going to focus on the last type of bond, which are alkynes. Alkynes, again, have to do with triple bonds, so that is a triple bond occurring between 2 carbons. These really follow the same name structures and everything as alkenes do. So if we go through and draw ethine, well, this would look like eth meaning 2 carbon. So we are going to have 2 carbon bonded together. And then ine meaning that there's a triple bond between them. And then we just have to add on our hydrogen. Well, in this case, both these carbons already have 1, 2, 3 bonds. So to get their 4 bonds that they want, they just need 1 more hydrogen. And that's what ethine would look like. And you notice our formula for this now is C2H2. Or we can go through and try 2-butyne. So but meaning 4. And if we draw this, I'm just going to draw the skeleton structure. Again, I didn't draw a skeleton structure over here because usually anything with less than 3 carbons, you really should draw the structural formula. Since this has 4 carbons, I'm just going to draw the skeleton formula. And this 2 indicates that the triple bond occurs on the 2nd carbon. So if we go through and draw this one, it's going to look like this, and that's actually, this one works either way. I could either name this as my 1st carbon, 2nd, 3rd, and 4th, or I could name this as my 1st, 2nd, 3rd, and 4th. And you'll notice that regardless of which way I count, the triple bond ends up starting on the 2nd carbon. So I go 1, 2, 3, 4, starts on the second carbon, or 1, 2, 3, 4 still starts on the second carbon. So 2-butyne is my correct name. And now we want to go through and figure out our formula for this. Well, this carbon only has this one bond here, so this one is going to need, and I'll just pick a different color here. This one needs 3 hydrogen. And now, if you look at this carbon and this one actually has 1 bond, 2, 3, 4 bonds already, so there's no hydrogens connected here. If we look at this carbon, there's 1, 2, 3, 4 bonds, so there's no hydrogens connected here. Now if we focus on our 4th carbon, it only has this 1 bond, so therefore it needs 3 more bonds, so that means there's going to be 3 hydrogens connected there. And that means our formula is going to be C4H6. Now I would like you to please pause the video and try to draw these next 2 structures on your own. Alright, now that you have tried to draw these on your own, let's go through and draw these ones. So again, we have the prefix of prop, which means we have 3 carbons. N is propyne, so this means we have a triple bond. It's not indicated anywhere, it's not indicated on being on a specific carbon number, so therefore we draw this as like this. And that means that this is our first carbon. We don't need to draw the 1 there because, like often in chemistry, when it's a 1, we just ignore it. And so that was what propyne would look like. And if we come up with a formula for that, this carbon has 1, 2, 3 bonds, so it wants 1 more. Therefore, this is going to need 1 hydrogen. This carbon is going to have 1, 2, 3, 4 bonds, so that doesn't need any hydrogens. And this last carbon here only has 1 bond, so that is going to want 3 hydrogens. And that gives us the formula of C3H4. And now this last one can be a little bit more challenging, but if we break it down, it's not so bad. So if we look at it, we have penta, meaning 5 total carbons, and if we want, just start off and draw the 5 carbons. And then it says it is diene. Again, this di here just means that there are 2 triple bonds occurring, and ine meaning triple bonds. So if we go through and draw these, it means that 1 triple bond occurs on the 1st carbon, 1 occurs on the 4th carbon. And I just want to go through and number these. So I'm going to say this is 1st, 2nd, 3rd, 4th, and 5th. And then we need to draw in our triple bonds. So we're going to have 1 starting on our 1st carbon, and then another triple bond starting on our 4th carbon. And then we want to figure out our structure. So this carbon has 1, 2, 3 bonds, therefore it is going to need 1 hydrogen. This carbon is going to have 1, 2, 3, 4 bonds already, so it's good. This carbon has 1 bond here, 1 bond here, and therefore it is going to need 2 hydrogens. And then we have carbon number 4 has 1, 2, 3, 4 bonds already, so therefore that one's good. And this 5th carbon has 1, 2, 3 bonds, so it's going to need 1 more. And if we go through and write out our structure, that means we have a structure of C5H4. Alright, I know these notes have seemed like a lot so far because there's a lot to them, but I would like you to please pause the video and go through and try and name these structures on your own. Alright, now that you have tried to name these structures, let's go through and see if we can figure out the name. First, I always like to start off by determining if they are an ane, which have single bond, ene, which have a double bond, or ine, which have a triple bond. So if we look at this first structure right here, well, this has no double bonds or triple bonds, they're all single, so therefore this is going to be an ane molecule, and then we count our number of carbons. There is 1, 2, 3, 4, 5, 6 carbons, so our prefix for 6 is hex. They're all double bonded, so it is ane. And there we go, that first one is now named. If we look at the second one, we have this triple bond here. So this is going to be an ine ending. We count our number of carbons, which is 1, 2, 3. And so we know that this is going to be prop. And since we only have the one triple bond, we don't need any sort of prefix here. And since it occurs on, and we're going to call this our first carbon over here, not our third, we don't have to write any number over here either, because when it's on the first carbon, we don't need to indicate that, so this is just propyne. Now if we look at the third structure over here, we start off by determining what type of bond it is. Since this has double bonds, it is going to be an ene ending. And then we count our number of carbons, which is 1, 2, 3, 4, 5, so that is going to be penta. And now comes the part where it gets to be a little bit tougher for students. So we have 1, 2 double bonds, which means we need to put this di prefix in here. Because what this di does is it tells us how many of this ending we have. Coming up in this unit, we're going to start to learn about alcohols and aldehydes and all these different types of endings. So we need to indicate how many we have. And you need to make sure that the di, that the prefix for that, goes before what it's indicating. Since ene indicates a double bond, the di goes before that. We can't say dipentaene because that's a completely different structure that you'll learn about in a few days. And now the last part is if I have this di here, meaning I have 2 double bonds, we need to indicate where those double bonds occur. Remember, we always want our lowest numbers, so I don't want to start from over here. I would actually want to start from the other side. So I'm going to start and say that's carbon 1, 2, 3, 4, 5. And therefore, this first double bond occurs on the first carbon. Second double bond occurs or starts on the third carbon. So the structure is going to be 1, 3, pentadiene. And when you label these, you always want to say, start with a 1, comma, 3, or whichever numbers they start on, and then you put this hyphen in between the numbers. So it says 1, comma, 3, hyphen, pentadiene. And now if we look at this last structure here, we start off by saying it is a triple bond, so it's going to end in an ine ending. Then we count our number of carbons, 1, 2, 3, 4, 5, 6. So our prefix for 6 is hex. So this is going to be hex or hexa. And then we only have one double bond, so we do not need any sort of prefix, prefix. We don't need anything in between our hexa and ine because we just have the one bond here. And then we need to indicate where does that start. Since it's not starting on our first carbon, we have to figure out, well, what carbon does it start on? So we have to check from both sides. If we number this could be 1, 2, 3, 4, 5, 6. Or if we start from this side, it could be 1, 2, 3, 4, 5, 6. Either way, you're noticing that the triple bond occurs on the third carbon. So we can just label this as 3-hexaine, or 3-hexine. So realistically, I should rewrite this. And I'm not too picky if you have this A in there, but usually since it's going from a soft sound to a soft sound, you would just call this 3-hexine. Or you could think of it as going from a vowel to a vowel. So the real name for this should be 3-hexine. I know this unit seems like a lot already. There's a lot to it. It is very specific, but please make sure that you are practicing this on your homework.